In the previous video, we dealt with odd and even functions, but you may be asked to prove algebraically that a function is odd or even. Now you'll remember that the definition was if the function was even, that meant that f of x was equal to f of negative x. That means you had a graph which looked like this. It was symmetrical on both sides of the y-axis. If you put in a value for x that was positive, you'd get a certain y value. If you put in the negative equivalent of that value, you get the same y value. So the y height of a positive and a negative number would end up being the same. And if the function was odd, the rule would be you'd have f of x is equal to negative f of negative x. That means you'd have a function which was symmetrical around the origin, which means what you get on this side on the right-hand side of the x-axis would be the mirror image flip of what you had on the left side. That means what you have on the right-hand side, if you were to flip it over here and then flip it down again, you'd find that this curve here exactly matched this curve here. Now, how do we actually go about proving algebraically that a function is odd or even? And what does it even mean to prove it algebraically? Why would one even care? Let's take a concrete example. Let's take negative 3x squared plus 4. And we'd like to prove that this is indeed an even function. If I put it into my calculator, I would get a graph which looked like this, more or less. And since I see that the only exponential power we have here is raised to an even number, in fact, I'm dead certain that this is going to be an even function. But proving means showing that it's not only even in this case or that case, but in every single possible case with no exceptions. If it was an even function, f of x would be equal to f at negative x. So if I put in f at 1, I would get negative 3 times 1 squared plus 4. And if this was indeed an even function, this would be the same as f of negative 1, which would be equal to negative 3 times negative 1 squared plus 4. And when we actually crunch the numbers, we get negative 3 times 1 squared is times 1 plus 4. Okay, negative 3 times 1 is negative 3 plus 4, which is 4 minus 3, which is equal to 1. Is that equal to what we have on this side? Well, let's see. We've got a negative 3, and when we square a negative 1, that's negative 1 times negative 1. That turns it into a positive 1. So we've got a negative 3 times positive 1 plus 4. And when we multiply that out, we've got negative 3. Negative 3 times 1 is negative 3 plus 4. And 4 minus 3 is equal to 1. So we've got 1 equals 1. So according to our test, this is indeed an even function. But that's not yet a proof. A proof means showing that it's going to work not only for this number or that number, but for any old number without any exceptions. What we need to do is come up with something we can plug into both sides of our equation here and show that it's still going to work out exactly as we intended. So here's our equation again. f of x equals negative 3x squared plus 4. And the symbol we're going to use to represent any number at all is x. So let's say f of x is equal to negative 3 times x squared plus 4. Now, you may be thinking that's pretty silly. All I did was add a couple of parentheses. Why did I even bother? Well, let's continue and then you'll see. We're saying that this is going to be the same as f of negative x, which in this case is equal to negative 3 times negative x squared plus 4. And when we perform all the operations, that's going to be negative 3. Well, x to the second power is x squared, so it's going to be negative 3 times x squared plus 4. And we're hoping that's going to be equal to negative 3. And when we multiply negative x times negative x, that gives us an x squared, but a negative times a negative turns it into a positive. So it's going to be negative 3 times positive x squared plus 4. So we have on this side of the equation for f of x 3x squared plus 4, and on this side for f of negative x we've got negative 3x squared plus 4. So what we've done is we've created a mathematical proof. We've shown that for a abstracted version, a kind of a blank check, an everyman, a mere symbol, in this case x, we got the same answer, 3x squared plus 4, negative 3x squared plus 4 and negative 3x squared plus 4 on both sides of the equation. Let's see now if the same style of proof holds good if we're addressing a odd function. For the odd function, let's use 2x cubed minus 4x. Now, if you put this in a graphing calculator, you'd get a graph which looked something like this. And if you substituted some numbers, let's say we, for our f of x, we put in f at 1 and f at negative 1, just to show you what works if we try an individual number. This would be 2 times 1 cubed minus 4 times 1, which 2 times 1 cubed would still be 2. And negative 4 times 1 would be minus 4, and 2 minus 4 would give us a negative 2. Now, if we put in the negative equivalent of this x value, a negative 1, we should get the negative of this. We should get a positive 2. And let's see if we actually get that. If we put in 2 times negative 1 cubed minus 4 times negative 1, well, 2 times negative 1. Negative 1 cubed would still be negative 1 because 1 is still 1 no matter how many times you multiply it by itself. And any negative number raised to a odd power stays negative. So we still have 2 times negative 1, which gives us a negative 2. That's it, negative 2. And minus 4 times minus 1, well, 4 times 1 is 4, but a negative times a negative is a positive. So we'd have here a positive 4. We'd have a negative 2 plus 4, and that would give us a positive 2. So it does look like we really do have an odd function here. We have that nice symmetry around the origin so far as we can see, and when we try a number, we get the same quantity with the opposite sign. But let's try and make this a real proof. The formula for an odd function is f of x is equal to the negative of f of negative x. That means if we have our function as it is, 2x cubed minus 4x, this f, we should get the negative equivalent of that. We should end up with negative 2x cubed plus 4x if we put in a negative x instead of a positive x. So let's see if that really works out. So this is what our results should look like if it's absolutely, universally, and always an odd function. So let's just substitute an x to begin with. So that would be 2 times x cubed minus 4 times x, and x, sorry, that should be cubed. X to the third power is x cubed. 2 times x cubed is 2x cubed. And minus 4 times x is minus 4x, minus 4x. So this side of the equation checks out. Now let's see what happens when we substitute a negative x. Do we get the negative of our original function? So let's take the original function, 2, and substituting a negative x times negative x raised to the third power minus 4 times negative x. We've got the same original function, but we substituted this time a negative x instead of an x. So we've got 2 times, now x to the third power is going to be x cubed, and any negative raised to an odd power remains negative. So we've got 2 times negative x cubed, and we've got a minus 4 times minus x. 4 times x is 4x, but a minus times a minus is a plus. Now, if we just perform this last bit of multiplication, 2 times negative x cubed is negative 2x cubed, and this is already in final form, plus 4x. So what we have on this side, when we put in a negative x, f at negative x, is the negative equivalent of what we had here when we put in a positive x. The 2x cubed became a negative 2x cubed, that should be, and the negative 4x became a positive 2x. So we have proved now algebraically that the outcome of this equation, when you change the sign of the input, if you keep the input the same but just change the sign, you're going to get the same output, but all the values will be reversed from negative to positive and positive to negative.